Within the physics body nodes, there is one that truly lives up to the title, allowing for all kinds of dynamic props and assets. But how does it work? What are rigid bodies? Well, put shortly, they are the node type whose movement is driven by Godot's physics engine. This is great as it allows you, the developer, to implement complex behavior with a lot less, at least relatively, effort than it would to do from scratch. So how do we go about implementing said behavior? Well, the best place to start would be with the rigid body's surprisingly long list of variables, all of which help tell the physics engine how to make the body behave and can be generally split into two categories: motion variables and simulation variables, the former directly impacting what would be the body's physical properties, and the latter modifying things like what kind of data is retrieved from collisions and what mode the simulation is on. So let's go over these, starting with the aforementioned motion variables, more specifically linear velocity, which stays true to its real-world definition, being a vector representing the body's movement. This movement will be in either pixels per second for 2D or units per second in 3D, with said units being equivalent to meters. Past that is linear velocity's rotational counterpart, angular velocity, being either a float in 2D or a vector in 3D that represents rotations per second. Both these variables can be used as speedometers or even edited directly to set their corresponding velocity. Though it's not generally a good idea to change these variables or others, such as position, during runtime unless you're setting them immediately when the body spawns or doing it very sporadically, as rapidly changing them within process, physics process, or other such functions can confuse the physics engine and cause all kinds of weird, unpredictable behavior. That all having been said, it is possible to indirectly influence these velocities through some of the rigid body's unique functions, such as apply impulse, which we'll touch on later in this video. But before that, there are still a lot of variables left to cover, like two related variables in linear and angular dampening, both of which being floats set to -1 that reduce the respective type of movement until the body stops moving completely based on how big a value you set it to. This can be really important as it helps make bodies go to sleep, which helps performance. And another important thing to keep in mind about this variable is that its default of -1 is just a placeholder for the actual default, which is set within the project settings under the appropriate section 2D or 3D of the physics tab. Moving on from there, we have another motion variable, gravity scale, a float that simply multiplies the intensity of gravity on the body, allowing you to even reverse gravity using negatives or negate gravity altogether with a 0. Said gravity itself can be changed if we venture back to the aforementioned 3D or 2D section of the physics tab in the project settings. Inside, you'll find their corresponding default gravity and gravity vector, the former effectively being how many units per second rigid bodies will accelerate with gravity, and the latter being the vector said acceleration will be multiplied by, giving it a direction. Make sure that when you change the gravity vector, you also normalize it, as otherwise it'll cause the gravity to be stronger or weaker than normal. And with gravity, there is, of course, weight and mass. The mass variable doing exactly what it does in real life, with more mass equaling more weight, inertia, and momentum. While the weight variable is effectively just a helper to make it easier for you to interpret what a set quantity of mass would weigh in kilograms based on the previously mentioned default gravity variable. Following on after that, we have a rather interesting variable, the physics material override, which allows you to assign a physics material to the body. Said material contains the bounce and friction variables along with their modifiers. These play a huge part in how collisions between bodies are calculated, with the math behind said collisions being a bit beyond the scope of this video. Though that having been said, the whole point of using a game engine with built-in physics is being able to use said physics without being a math major. So I'm still going to dive into the surface level of how these variables work, starting with the more simplistic of the two, friction. A float that, of course, effectively works the way it does in real life, causing the body to decelerate when sliding against another, with the default of 1 causing maximum deceleration and 0 causing no deceleration at all. There is also a modifier variable for friction, simply called rough, a bool that changes the priority of whose friction between two colliding bodies is used. Normally, whatever friction is the lowest is the one used, but when one body has rough set to true, that body's friction will always be used for collision calculation. And if there is a collision between two bodies that both have rough set to true, the engine will use whatever friction is highest. But what do you do if maximum friction on its own doesn't cause enough deceleration? Well, that means you need to increase the force pushing said body into whatever it's sliding against, either by increasing the body's gravity scale or applying your own custom force. Doing this significantly increases friction's impact. Then next up is bounce, another float ranging between 1 and 0, this time representing how bouncy the body's collisions will be. Now, I imagine you intuitively have an idea of what that means. After all, who hasn't played with a bouncy ball before? But what does bounce mean to the physics engine itself? Well, it's actually a measure of how elastic or inelastic collisions will be. A perfectly elastic collision, in our case a collision with a bounce of 1, is where all kinetic energy is preserved. While a totally inelastic collision, a collision with a bounce of 0, doesn't really care about preserving kinetic energy at all. The easiest way to see this effect in action is by just letting several rigid bodies with no linear dampening fall onto a static body. You'll see the fully elastic body bounce really high and continue bouncing forever, while each subsequent body with reduced elasticity will bounce lower and not as much, until the final completely inelastic one doesn't bounce at all. This bounciness is caused by static bodies having, as far as the physics simulation is concerned, infinite mass, meaning that they completely resist any would-be transfers of kinetic energy, though the energy preserved in elastic collisions still has to go somewhere, so it's reflected back into the rigid body. This also happens in collisions between rigid bodies with different masses. Another factor in these collisions is that when bodies collide, their bounce values will be added together, still all maxing out at 1. That's why if two bodies with a bounce of 0.8 collide, it acts the same as it would if only one of them had a bounce value of 1. And that's where the modifier variable absorbent comes in, being a bool which causes the body to absorb or subtract its bounce from the total bounce value of any collision. If a body with absorbent collides with a body that doesn't have any bounce, then the collision will act as normal. So at least to say, if you use these properties, make sure to thoroughly test and tweak them to make sure everything works the way you intend. Also, on that note, the nice thing about these variables being attached to a material is that it gives you an easy way to make sure these variables are consistent between different assets, which is done by saving the material and then applying it across said assets. This makes it so that when you change these variables on one asset, it changes them on all assets. After that, the only variables left are all either 2D or 3D exclusive, starting with 2D's applied force, a vector that's used to apply a constant force to the body. This is great for doing things like simulating drag or wind blowing on said body. There's also an angular counterpart to this variable, applied torque, this time being a float that, of course, applies a constant torque to the body. The other 2D exclusive variable, the float called Inertia, isn't actually shown in the inspector. Within the context of the physics engine, this inertia variable is basically the rotational equivalent to mass, in that it determines how much torque it would take to rotate the body. And this variable is hidden because it's typically calculated at runtime by the engine, but it can be set directly via a script. If you do decide to give it a custom value, remember that resetting it to 0 will return it to being automatically calculated by the engine. Now on the other side of the spectrum are the 3D exclusive variables, being the angular and linear lock variables. These are two sets of 3 booleans that lock their respective kind of motion on a given axis. This is every bit as useful as it sounds, especially for creating what would traditionally be a 2D game like a 2D platformer with 3D graphics. And with that, we can finally move on to the simulation variables, starting with sleeping. A bool that, when true, causes the engine to stop running physics calculations on the body until some kind of force, be it from a script or a collision, is applied to it, resetting it to false. This can be a godsend for game performance, particularly when there are a lot of rigid bodies all in one scene. To go along with that is another bool variable, can sleep, which is defaulted to true. This variable is important as it's effectively what controls if the engine can put the body to sleep on its own. This happens after the body has sat below specific movement thresholds for a set period of time. In 2D, these thresholds can be modified within the physics tab of the project settings. However, in 3D, these settings do also technically exist, but you have to directly access and modify the physics server from within a script to change them. That having been said, the default settings are typically going to be good enough. There's also a signal related to these variables, sleeping state changed, that is emitted every time the sleeping variable is changed. Then next up is another duo of properties, this time being contact monitor and contacts reported. A bool and integer respectively, with the former controlling if the body will emit the body and body shape entered exited signals when it comes into contact with another body, and the latter controlling how many of these signals can be emitted. Even if the body makes contact with multiple other bodies at once, there will only be as many signals as contacts reported calls for, so keep that in mind. Now about those aforementioned signals. They can be put into two categories based on what information the signals carry, with the body signals simply returning a reference to the body the subject collided with, while the body shape signals are meant for more advanced use cases, returning much more information, being the collided body's resource ID, aforementioned body reference, collision shape physics server index, and the subject's collision shape physics server index. These signals also come in two types based upon their emit conditions. The enter type emit upon initial contact, and the exited type emit once said contact has stopped. So from there, I guess I should go into continuous CD, a list of options in 2D and a simple bool in 3D that controls if the body will use standard collision detection or the more advanced and taxing continuous collision detection. This continuous collision detection, which I'll abbreviate as CCD, is meant to keep bodies who are moving extremely fast from missing contacts with other bodies, and passing through them between physics frames in what's known as the tunneling effect. Said effect is common to real-time physics simulations, and is even regularly exploited by speedrunners, being caused by the discrete way these simulations detect collisions, which is to just displace a body by an amount proportional to their velocity and then check post-displacement if it's intersecting any other bodies. Then if it is, the body registers that as a collision and its position is corrected so that it no longer intersects any of them. This is typically fine, but as stated, if the body is moving extremely fast, it may end up on the other side of another body post-displacement, and since the bodies never intersect, the collision won't be registered, effectively causing the moving body to teleport or tunnel through the other. CCD usually fixes this via either a shapecast or a raycast between the position said body was in at the beginning of the physics step and the position it was in at the end of it, catching potentially missed contacts, with the shapecast version being extremely accurate but computationally taxing, while the raycast version is less computationally taxing at the cost of being less accurate. Alright, so that should be how CCD and collision detection in general works within Godot. But, all that having been said, at the time of making this video, CCD seems to be somewhat broken. Now, if you're not interested in hearing how it's broken, or I've posted a comment saying it's been fixed, you can go ahead and skip the time on screen. But for those of you that are curious, let's see what I mean. As said earlier, continuous CD is a list in 2D with three options: disabled, the default setting, cast ray, and cast shape, which sounds great as both of the previously described CCD methods are represented here. But only cast ray actually seems to work, as you can see here where I have a rigid body with a really strong force pushing it into the wall. The situation is even stranger in 3D though, as not only is continuous CD just a bool, which leaves us with no idea as to what kind of CCD it would be using, it's also always active. So no matter how strong of a force I have pushing on it, or how arbitrarily high I set the velocity, it just won't tunnel through, regardless of if CCD is true or false. Weirdly though, when the body has multiple collision shapes, it will behave in the opposite way, with CCD always being disabled. So yeah, Godot's CCD, particularly in 3D, is a bit of a mess. That all having been said though, this is a well-known issue, so I'm sure by the time 4.0 comes out, it'll probably be fixed. Just make sure to be conscious of the issue until then. Now with all that out of the way, we can move on to the second to last variable, mode. A list of options, those being rigid, character, kinematic, and static, with each successive option simplifying the body's behavior more than the last. Rigid is of course the default setting and most complex, followed by character, which allows the body to move as normal, but completely stops any rotation. This is, as its name suggests, great for making rigid body characters, as you typically wouldn't want them falling over and rolling all over the place when moving around. The final two, kinematic and static, can actually be a little confusing. Both stop the body from rotating and moving, so what's the difference? Well, your first thought, like mine, may have been that kinematic mode gives you access to the kinematic body's move and series of functions, as that's the only difference between static and kinematic bodies. Which is technically true, but the actual difference between these nodes is the kinematic mode being able to detect contacts and emit the associated signals, whereas static cannot. This is a reference to the fact that through the move and functions, kinematic bodies can also detect collisions. Switching between these modes can have a multitude of uses, like making players ragdoll when killed, teleporting objects, making falling floors, etc. And we're finally here, the last variable in the rigid body node, custom integrator. A bool defaulted to false that, when turned on, disables the body's internal force integration. This means it will ignore any forces applied to it outside of the integrate forces function and collisions, allowing you to have complete control over how the body behaves. Speaking of which, let's finally move on to functions, starting with the previously mentioned integrate forces, which, unlike the rest of rigid body's unique functions, isn't meant to be used within process, physics process, or etc. Rather, it's effectively another process function that's automatically called by the engine, which gives you a reference to the body's physics state. Which is neat, but why is it useful? Well, remember back when I was going over linear and angular velocity, and how it was a bad idea to directly modify said variables and others like position at runtime because it could confuse the physics engine? This is how we get around the limitation. Because when we modify the body's state, we're directly telling the physics engine what to do when processing the simulation of the body. Now, the physics state itself is actually its own thing that, while sharing several variables and functions with rigid bodies, actually has many that are unique and some that are missing, which moves it a bit outside the scope of this video, though I do want to specifically mention that it doesn't have position or rotation. It instead just has transform, which you'll have to modify to change the body's location and rotation. If you would like an entire video diving more into the physics state, let me know down in the comments. Anyway, now we can move on to the more standard functions, starting with add torque, add central force, and add force. In 2D, these functions literally just add to the applied variables based on their arguments, with add torque and add central force directly adding to said variables, while add force counterintuitively adds to both in order to emulate a force that's being applied with an offset defined in its first argument. In 3D, things are a bit different due to 3D rigid bodies not having the applied variables. This means that where you would have wanted to call the appropriate function only once to constantly apply a force in 2D, you instead have to call it every frame in 3D. Another more minor difference between these functions is the 3D version of add force has its arguments swapped around, with the offset vector being the second argument and the force vector being the first. Following them are the impulse functions, which are similar to the previous in that they're another way to move the body, but whereas the add functions are meant for constant sustained movement or acceleration, these are more meant to simulate one-time impacts or impulses, per their namesake. Imagine them as flickering a thruster or hitting a pool ball with a cue stick. And just like previously, these functions come in two flavors. Apply central impulse and apply torque impulse, both taking a single vector as an argument and applying either a linear or angular impulse to the body's origin based on said vector. While apply impulse takes two vector arguments, applying a linear impulse based on the second vector with an offset based on the first vector. After those, we have set axis velocity, which may seem, at first glance, to be redundant as we can already set the body's velocity along any of its axes by just directly editing its velocity variable. But no, the way this works is actually far more interesting than its name would lead you to believe. See, this method takes a single vector as an argument and uses that vector's direction to effectively define an imaginary axis, and then modifies the body's linear velocity to where, if it had said axis, its velocity on that axis would equal the given vector's magnitude. This is useful because the velocity in directions perpendicular to our imaginary axis will be preserved. Same as if we change the real x-axis velocity without changing y or z's velocity. And that leaves us with the last of the standard functions that share between 2D and 3D, the aptly named get colliding bodies function, which does exactly what one would expect, returning a list of physics bodies the body came into contact with during the last physics step. Said list's maximum size is determined by the contact's reported variable, and only works at all when you have contact monitor set to true. So with that, we can move on to our last function and only 2D exclusive. Test motion. Being made of 4 arguments, does what one would expect. Check to see if, had the body moved along the vector provided in its first argument, the body would have collided with any other physics bodies, returning a bool representing the result. Of course, there is a good bit more nuance to this function though, thanks to its other arguments, with its second being a bool representing if the test movement would have infinite inertia, which, while left on its default of true, makes said test movement ignore other rigid bodies, only detecting kinematic and static bodies, while when changed to false, it will detect all physics bodies. The third argument is the simple float defaulted to 0.08, representing the collision margin this movement would use. Or in other words, this is the amount the body's collision shape would be inflated to help make sure it doesn't accidentally miss any collisions. It's generally a good idea to have a margin, and the default value is subpixel in size, so it shouldn't produce any false positives. With that in mind, I definitely recommend you leave it at its default unless you specifically run into issues. Next up is the last argument, being defaulted to null, and also a bit confusing as it works significantly differently from how most arguments work. Starting with the fact that in order to use this argument, you have to first create a variable that's a new physics 2D test motion result. a class of object that's specifically meant to hold data for 2D rigid body test motions. Then, plug that variable into the argument. Now, when you later reference this variable, it will contain all the more specific data relevant to the potential detected collision, such as a reference to the cladding body, the normal of said collision, point of contact, and so on. One very important thing to keep in mind with this function is that you can set its first argument to all zeros and it'll still work. This can be really useful for collecting specific data on other bodies the rigid body is already colliding with. And that's it. Pretty much all you'll need to know about rigid bodies and how to use them. If you have any suggestions for future content or advice or criticisms, feel free to leave them in the comment section. And until next time, thanks for watching.